This video is about correlation, and it will start with the relationship of x and y. X is the independent variable, and y is the dependent variable. This has been introduced in high school, so long story short, the independent variable is in the x-axis, and that's the horizontal line. These are usually the variables that are the predictors or the inputs or the causes of something. Dependent variable is in the y-axis, that's the vertical line. It is often called the response, the output, or the effect. In this example, age is the independent variable. Elizabeth's age will come no matter what we do, and tied to her age is her height, which happens because of her aging. In this other example, weeks is the independent variable and time will march forward, and books will be sold in respect to time. In data where one variable is the measurement of time, that data usually goes to the x-axis. Now that we know what x and y are, in this module we will figure out their correlation. Correlation is a statistical measure that expresses the extent to which two variables are linearly related. It quantifies the direction and strength of the relationship between the two variables. Now let's break down this definition. The variables are the two data that are gathered. And then we assign x and y. The linearly related means that we will solve a certain value that tells us how much they are related. Direction and strength will tell us if this specific line will be up or down, or big or small. The correlation coefficient of this example is positive 0.85. Since it's positive, it goes up, and since it's closer to 1, it is big. This other example, as you can see, makes us think that the variables are not very harmonious with one another. This axis variables up is another axis variables down. There's not much pattern to it, it looks chaotic, so it makes sense that the calculated correlation coefficient is actually 0.20 and it's negative, meaning it goes down. Let's look at the other graphs. There are graphs that has strong correlation, meaning coefficient closer to 1, but are negatively correlated. Negatively means the higher the x-axis is, the lower the y-axis would be. There are zero correlation, and their scatter plot looks absolutely shapeless. Now let's look at this data. This table shows the average temperature per month of a very cold country. So in summer, it goes up to 22 degrees. There's 22.9, and it's quite high for them. And the warm temperatures are from June to August. And in wintertime, it goes as low as 1.2 degrees Celsius. As you can see here, ice cream production is also gathered, and let's say the ice cream production is related to the demand. Then maybe we can hypothesize that the production is greater when the temperature is higher. Putting that in a scatter plot, x is plotted horizontally and y is vertically. And in this graph, we can see that there is a trend. In higher temperatures, the productions do increase. This data has a correlation of 0.7180. Now, where do we get this value? It's by using this formula. Now, let's break this formula down. This is the previous example. Let's solve for the correlation coefficient of this one. Let's break down this formula to understand all their elements. So the first thing we have to do is get the averages. So that's the x bar and the y bar. The x bar is 11.7 and the y bar is 66,436.42. After getting the averages per variable, we're going to subtract it to each of the observation of that specific variable, and that's how we're gonna get xi minus x bar. We're going to do the same for the variable y. So negative 10,494.42 is from 55,942 minus 66,436.42, and you just have to do the same for the rest. The next breakdown of the formula is the entire numerator, and that is the product of the first two columns. Negative 10.50 multiplied to 10,494.42 is 110,191.38. And according to the formula, we need to get the summation of this column. So the grand total of this is 636,058.80. The next part of the formula will be the denominator. So we're gonna get this group, and that is just the first column with a square. In the new column, get the squares of the first column. Like in this observation, the square of 10.50 is 110.25. Do the same for the y variable. Make a new column which will consist of the squares of the second column. Like in this observation, the square of 10,000 is 100 million. And then we will get the summation of both of these columns. For the fourth column, the x, we get 750. And for the fifth column, we get 1 billion. Now that we have all the sums that we need, let's plug it to the formula. And we get 0.7280. Aside from knowing how correlated two variables are, we can use the correlation coefficient in hypothesis testing, and we will use this formula. This formula will give us the standardized test statistic for correlation hypothesis, and of course, that means the critical value will come from the t-table. First step is, of course, get the null and alternative hypothesis. For correlation, we're always assuming that there will be no correlation between the temperature and ice cream production, and we're going to test if there is any correlation between these two variables. The null and alternative will always be no correlation and yes correlation, respectively. Always remember that in hypothesis, the mathematical expression will always be in population. Rho is the population version of R, which is the correlation coefficient that we solve. The null is rho equals 0, while the alternative is rho not equals 0. This is always two-tailed because there is negative and positive correlation, and we look at both sides. First step, do we get the important values to get the critical value, and that's the level of significance and the degrees of freedom. The degrees of freedom will come from n minus 1, and since we have 12 months of data, our degrees of freedom is 11 here. The critical value will come from this table. I hope by now you already know how to get the critical values. So given a two-tailed table and then a 0.05 level significance and degrees of freedom of 11, we get 2.2. First step for the standardized test statistic is 3.42, and that came from this formula. This formula gives us the t-value, and this r comes from the correlation coefficient a while ago. Now let's sketch it out. The decision will come from the fact that the standardized test statistic is greater than the positive side of the critical value. So that means we must reject the null hypothesis because 3.42 entered the rejection region. So it seems there is correlation between temperature and ice cream production. There is an easier way for us to calculate the correlation coefficient. So what we did a while ago was manual. You can use Excel from your PC or from your mobile. So you just plug in the values here. And then in an empty cell, type in equal sign CORREL, open parenthesis, and then select the X array. Do not include the labels, and then comma the next array. Press enter and you get 0.7180. You can also get the critical value in Excel, and the code would be equal sign t.inv.2t open parenthesis, the probability of 0.05, and then the degrees of freedom. And there you get 2.2.